So hello everyone and welcome back to this next lecture in the DC-DC converter series, and we have been simulating the transformer. So where we had left off last time was we were trying to simulate a high frequency transformer but with the same time step as a normal transformer. So we had used the same 1 microsecond sampling time step of the control file as well as a 1 microsecond integration time step of the simulation, right? But the frequency rating of the transformer was chosen to be 10,000 hertz, right? And the result of that was we were getting an unstable simulation. So in this lecture, we will examine the reason for this instability and how do we solve this instability. So these are some of the issues when you do solve high frequency systems and what you need to solve them, right? So let's go back to the browser. And before I start this lecture, as usual, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I do have a full-length course on the MOOC website Udemy. And the very first course I created was simulating power electronic circuits using Python. And in this, I talk about the basics of Python, how to install Python power electronics, some basic theory of electrical engineering and power electronics, and finally a case study of how to simulate a buck converter with closed loop PI control. And the next course which I have is more on the signal processing side. It's called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use, or rather the basics of signal processing, how you can use Python in signal processing, what are the Python packages, and finally there is a case study of how you can design a low pass and a notch filter using frequency response characteristics with Python packages like NumPy and SciPy. And the latest course which I have is what is called Simulation of Magnetics for Power Electronics using Python. And in this, I talk about how the basics of magnetic modeling and how you can simulate an inductor, a coupled inductor, and a transformer using Python power electronics. And there is eventually a case study of a flyback converter. So the links for these courses are provided in the description for this video. So if you're interested, please do check it out. Anyway, coming back to the actual lecture. Now, to be able to find out what is actually happening at this high frequency, let's look at what happens when this frequency rating changes. So the most important thing is we increased the frequency rating from 50 hertz, which was like a line frequency transformer, to 10,000 hertz, right? Now, when we did this, our simulation became unstable. So the first thing we need to see is what happens when we change the frequency. And the result is, and that answer is pretty obvious, that what changes is are these inductances. For example, frequency appears in the inductance because we are choosing the reactance as a percentage drop of the rated voltage. So we are saying that 1% of the rated voltage is dropped across the inductance, right? And therefore, this inductance, or rather the total self-inductance, causes a 1% current to flow through, and therefore we are calculating the actual self-inductance. And we are also calculating the leakage inductance with that. So now the question is, what happens when you change it? So for example, let me just go back to 50 and let me look at my equations. So in these equations, I have the self-inductance and I have the mutual inductance. So let's plot these and figure out what's happening with them. So let me come here and print L1, L2, M, and let me actually bring it here. And let me plot M12. Actually print it out, I'm not plotting it. So this way, let's see what's actually happening. So what I'm going to do, I'm going to go here and run the simulation. So let's go to the command line and you should see these inductances. So at least we don't see an error, we see this. So that's good. Simulation is running. So let's stop it. And let's go to the command line and let's copy these values. And let's go to our spreadsheet. Any one spreadsheet will do. and let's just paste it here, right? So these are our values. Now let's go back to our code, and this time let's go back to 10,000 Hertz. Right? So let's go back and run the simulation again. Let's go back to the command line. We see it's working. Let's go back to the web browser, stop the simulation, come back to the command line and copy these results. So I go back to the Excel sheet and I paste it here, right? So the idea behind this exercise was to compare our inductance. So what are we plotting? Let's go back to the code again and check. I am plotting self-inductance of winding 1, self-inductance of winding 2, and the mutual inductances between the two windings, right? So, and it is here. So if we compare, we see that in the first case with the 50 Hz transformer, the self-inductance of winding 1 is 1.833 Henry. This is with a 50 Hz transformer. Now with a 10,000 Hz transformer, this is the value you get. Your self-inductance of winding 1 is now 0.009 Henry, which means it's 9 millihenry, right? So if you take this and you compare, so let me just do this, 1.833 divided by 0.009. Actually, I should do the other way around. 0.009 divided by 1.833. So you see that this ratio is 0.004. When by increasing the frequency of the transformer, we have decreased our self-inductance by this ratio. Now, what does that mean? Let's go over to the transformer circuit and let's see what that means. Now, this self-inductance appears here. So this branch is the model of the transformer winding. So the self-inductance typically appears here, right? Now, we also have along the self-inductance, we have chosen a winding resistance, right? Now, what that means is that this branch is an inductance resistance circuit or an LR circuit, right? Now, an LR circuit has a time constant, right? Any LR circuit has a time constant. So what that means is, let me go back to the one which had it. Yeah. So what that means is this L by R ratio is the time constant of an inductance resistance circuit. When our time constant, or rather the inductance, decreases by this ratio, the time constant of the circuit also decreases by this ratio. What it means is now the circuit is prone to much faster oscillations. And when the circuit is prone to more faster oscillations, the result is you have now to simulate it much faster in order to be able to achieve a stable result. That is what has happened, right? So what this means is we are not simulating our circuit fast enough, and that is the reason why this circuit is becoming unstable. In the previous case, when we simulated a 50 Hz transformer subjected to 10,000 Hz, in that case we didn't have instability, we had an error. But now we have downright instability because our system is much faster, right? Because of the values of the inductances, our system itself inherently is prone to oscillations, and unless we capture those oscillations, we do not have a stable result. So the only way to solve it is to decrease the time step by this same magnitude, right? So what that means is we have a 1 microsecond time step. This 1 microsecond time step has to be changed in this same ratio. That is, it has to be changed in the ratio of 0.005. Alright, I've just rounded this 0.0049 to 0.005. So what this means is that we need a time step such as this in order to be able to simulate this system accurately, right? So let me see if my simulation is running. No, it is not. So first thing I'm going to do, I'm going to remove these print statements because otherwise they will clog up our command line. This is only for the purpose of visualization. We can now go actually to our simulation, and let's go back to the main edit simulation parameters. So here, the integration time step we will change to 5.0 e raised to minus 9, because that's what we arrived at. Because we said that because our simulation, because our system is now much faster, because our inductance is decreased by this level, therefore our time constants have also decreased by this factor. And therefore, if we have to simulate the system, our integration time step has to also decrease by this same factor, which resulted in this integration time step. So let's go back and change this. Now, you do not have to change it that much, but I still prefer to keep the time step of data storage the same, right? This is totally up to you. You could have something like 1 e raised to minus 7 or 1 e raised to minus 8. You can experiment with this, because remember, time step of data storage determines the resolution of your plot. So if you are convinced that your plot is accurate enough, you can increase it to be able to result in lower data sizes. That does help, but I will keep it the same for now. So let me simulate, save this, and go back to the main page, go to the view output. We have to also change it here in the control file. Alright, we need to change this as well. So I will change this to 5.0 e raised to minus 9. Right? So we are now simulating our entire system at a higher integration time step. That means a lower integration time step rather. So we are simulating faster, and we also have a faster control file, because this control file actually performs the numerical integration. So it has to match the actual time step. So with this change, let's go over and run the simulation. So let's go to the command line. We don't see any errors. This has stopped because I've removed the print statement. And here, let me come and plot the transformer currents. Now, because we are simulating at 5 e raised to minus 9, our simulation is going to be much slower, right? There's no way out of that. So you see, we do have a stable result, right? Now, it will take time to run. There's no way out of it. I will stop the simulation, or rather I will pause this video and come back when the simulation is done. So the simulation has been running for a few minutes now. So let me go and just make sure that there is no error in the command line. There is none. And let's go and plot the transformer currents. And we come, and you see we have the result. So now you see there is no instability, right? And as before, there is, you see, the primary current. Let me zoom in. So between 0.0015 and 0.002. There appears to be a bug in the code. Let me see what happened to the command line. For some reason, this hasn't come at all. There has been a bug. So this might be a bug with matplotlib. I'm not sure what actually causes it. Maybe it's too much of data, but let me plot it again. Yeah, now it's back again. So these bugs do appear. Actually, I forgot to put the zoom. And yeah, now we have a zoomed in current. So if we zoom in here, let me just expand this and zoom in, we see that the results are fairly similar, right? So as before, the orange line is the secondary current or the low voltage current, which is why the current is larger, right? The blue line is the primary or the high voltage winding, which is why the current is lower. But even though we have a 2:1 step down transformer, the primary current is not exactly half the secondary current. The reason for that is the magnetizing current, right? This is what we've already seen. And if you want to verify that, by all means, make the resistance on the secondary very large so that this secondary current is almost zero, and verify how much is the magnetizing current. That is an exercise I will leave for you. So with this, I will stop this lecture because, as I said, I do not want these lectures to get too long. If you have any doubts about what I did, please do comment on this video or post on social media or send me an email, whatever is your preference. Otherwise, I will see you in the next week where we will get started with the very basics of how we can use this with a power electronic circuit, right? So thank you so much for watching and see you soon. Goodbye for now.